UCLA is a world-leading institution for academic scholarship, where our mission to train the next generation of scientists and engineers goes hand in hand with building a vibrant and diverse research ecosystem. Partnerships like that between the California Nanosystems Institute and the Samueli School of Engineering allow us to provide shared research infrastructure, such as the UCLA Nanofabrication Laboratory, or the NanoLab as we call it. These open access user facilities are really a foundational element to the research enterprise at UCLA, whose impact extends far beyond simply providing equipment and services. We know that driving discovery and innovation requires far more than gaining access to the latest technology. So we invest in assembling a team of experts who not only have the technical know-how, but are also passionate about sharing this knowledge with others. Through this shared vision and our collective efforts, we look forward to breaking new ground and to truly redefine the leading edge of science across disciplines.
This is Subbu Iyer. I run the UCLA CHIPS group here at UCLA. And this is a consortium we have that is a UCLA-led partnership. So what we do at UCLA CHIPS is we look at two broad set of problems. There's the large-scale energy-efficient systems and the medical engineering applications. And we do that a combination of advanced packaging technologies and novel compute architectures. And we have three core technologies right now. One is silicon as a heterogeneous fine pitch packaging platform, and the second one is FlexTrate as a flexible biocompatible heterogeneous integration platform, and the CTT as an in-memory compute device. So what we're going to be talking to you today about is our students are going to be presenting the FlexTrate work that we're doing. Okay, and the idea of the FlexTrate is actually a very old idea with a twist. It's a bicycle chain. And if you look at this old good old rusty bicycle chain, we have this whole bunch of rigid links with hinge connections. And so what happens now actually is that even though the bicycle chain is fabricated with all these rigid connections, rigid links, the entire structure is quite flexible. And the idea here is that the rigid links are the chips and the flexible connections are the FlexTrate. And using that, we have this vision of building a multi-chip platform, a heterogeneously integrated platform, where we can actually do a lot of different things and make it all flexible for both medical applications as well as any other applications that require certain degree of flexibility. And my students will talk a lot about this in the videos that we're going to be showing you today. I want to actually thank all our sponsors, obviously, as well as the University of California, especially for their support. And of course, you will be seeing more of our students, and I want to also give a call out to our alumni, many of whom are now in industry and in academia, and they have actually done a marvelous job of putting us on the right track here. So thank you so much.
Hello, I am Arslan Alam, a senior electrical engineering PhD student, and I work on developing FlexTrate, which is a new approach of making flexible systems that is based on fan-out wafer-level packaging, or FOUL-P. FOUL-P is a popular technique for rigid packaging that we have modified to be used for flexible applications. In the FlexTrate process, we place the dies facing down on a thermal release adhesive on the first handler, dispense our flexible molding compound PDMS, and compression mold and cure by placing a second handler with another thermal release adhesive on top. After curing of our substrate, we thermally release the first handler and now have the dies facing up and embedded in PDMS while being supported on the second handler. We then deposit the dielectric layers, complete the metallization to connect the dies, passivate the system, and release the second handler, where we get our flexible platform FlexTrate, which has heterogeneous dies integrated without any solder. FlexTrate is bendable to small bending radii without any performance degradation. On FlexTrate, we have demonstrated 200 dies integrated at 40 micron pad pitches with wire widths less than the thickness of human hair. We have also shown a LED display that can be folded without any performance degradation. I am currently working with UCLA's David Geffen School of Medicine and California State University, Los Angeles to build a surface electromyography system on FlexTrate that we call FlexEMG. I have already demonstrated a highly flexible lightweight and easy to wear SEMG system that has up to 20 electrodes, filters, microcontroller, and wireless communication over Bluetooth. This device can reliably record muscle signals from up to 8 locations. We are targeting applications for this device in spine surgery monitoring, physiotherapy, and rehabilitation.
Hi, my name is Gautam. I'm a PhD student in the CHIPS lab at UCLA. My work focuses on gallium nitride microLED mass transfer and assembly onto flexible PDMS substrates to make high-resolution displays. These displays typically have more than 300 pixel per inch resolution, and the target applications are for AR, VR, as well as optogenetics. This technology, we call it as FlexPlay, and it leverages a mass transfer technique that we developed with Vico Instruments that uses adhesive bonding for high resolution, high precision, and yield pickup and transfer of microLEDs, along with our in-house developed FlexTrate process.
Hello, my name is Randall Irwin. I'm a PhD student in electrical engineering, and I've been with the CHIPS group since 2017. I'm developing a flexible connector for high-speed signal transmission, which we call FlexCon. This connector leverages the tight interconnect pitch of FlexTrate to achieve bandwidths of hundreds of gigabits per second per millimeter. We're targeting applications of external communication in wafer-scale systems, as well as chip-to-chip communication. I've also worked on a method of improving the thermal conductivity of FlexTrate by using nanowires dispersed in PDMS, which we weld together using microwave irradiation. We call this modified material TPDMS, which can assist with thermal management in FlexTrate.
My name is Guangqiu Yang, a PhD student from Material Science and Engineering. My work focuses on developing a flexible power solution using the FlexTrate platform, which we call FlexPower. FlexPower has high energy and power density, which can meet power requirements for most wearable devices. In FlexPower, small rechargeable thin-film batteries and power management system are heterogeneously integrated into FlexTrate to form a large matrix, which can conform to the complex topology of human body and maintain high performance even after thousands of bending cycles.